between 2001 and 2008. Originally, he got his PhD in condensed matter physics at the University of Illinois in Chicago. And as I said, he's been at Oregon for most of his career and has worked on a number of highly interesting things. He did major work in superconductors, vortices, magnetic flux imaging, and actually he's been widely recognized for these achievements with various awards. The R&D 100 award. He got the Condeling Honors Prize in 2003. Of course, his work on superconductors, particularly high-temperature superconductors, and he's a member of the National Academy of Science. In addition to all of his scientific accomplishments, he's also been a great advocate for research, and particularly research in sustainable energy. He has devoted a lot of effort to organizing efforts to get research in place to address important issues, for instance, related to the hydrogen economy. He was associate chair of a panel on the basic research needs for the hydrogen economy, and also he testified in front of Congress on that issue. And in the area of solar energy, again, he was chair of a workshop on research needs in that area, along with Nate Lewis from Caltech. I think we owe him all gratitude for devoting so much effort to promoting these important issues, and I hope we'll hear some more details about that in this talk today. Welcome.
Great, thanks so much, Chris. Yeah, it's great to be here. I think it's the second time or third time I've come to Santa Barbara. I have to tell you, and I'm sure you don't know this, that you have a beautiful campus. And you're living in paradise, and you don't know it. So I could say that as coming from Chicago, the comparison is really, I would say, striking. So I want to talk not about a technical subject, a particular technical subject, but about, this is on, isn't it? Yeah. About energy, which is a huge subject. Chris alluded to my involvement, and I was telling this story earlier today, but let me tell it again for everyone. 2002, people from DOE, in particular Basic Energy Sciences, called me and said, would you help us with this workshop on energy? And it happened to be the first workshop they held on this series. I thought to myself, no, I'm too busy for this, and I've got other things to do. I can't be distracted. But they were my sponsor, and I said, yes, I'd love to help you. Thanks for calling. And I went to it and found, to my surprise, that it was really quite intellectual. It was quite interesting, quite subtle, quite interdisciplinary, and full of competing tugs in terms of research, in terms of the economy, in terms of the environment that required careful thought. So it was not at all a trivial subject, as of course we all know now. And I began to get interested, and that was when I started to get interested. About 5 years ago, I got a lot more interested. And what I'm going to tell you today is a synthesis of, I would say, the research and development point of view of energy. So I want to start with a couple of, actually 3 drivers. Oil, in particular foreign oil. The economy, which is an issue right now and has been for the last 3 years and continues to be and will be. So recovery, economic growth, jobs, and carbon dioxide. I'm sure you know what that means in terms of climate. Then talk a little bit about sustainability. That's something we all love, hard not to like. It's like motherhood and apple pie, but we don't know what it means. So I'm going to give you 3 criteria for sustainability and ask you to judge which of the 3 or how many of them are relevant. And really one question that we have to answer as a country is, how sustainable should we be? As you can take sustainability to, let's say, the limit, and I think we would all agree that's probably too much. The other side of the spectrum is where we are right now, and I think most of us would agree that's not enough. So we need something in between. Then most of the talk will be on sustainable energy alternatives that we might do, and the science roadblocks or technical roadblocks that stand in the way, what needs to be solved. And finally, I want to say a little bit about educating the next generation of all kinds of people in particular at this UIC Summer Institute, which we launched last year and will continue. So first, here's some background reading. The written version of this talk is here. It was published in Physics World about 2 years ago. The talk is updated to some extent since then, but that's a good reference. Here's a more technical paper on the functionality of materials for sustainable energy, in particular superconductors, titanium dioxide and other semiconductors, and a few other things. That's about a year old. And this policy report, which came out a couple of months ago, it's an update of a report that came out the year before. It's written basically by Bill Gates and Jeff Immelt and others from the business side, and they're saying we need to do something about energy. In particular, to give you a flavor of what their recommendations are, they say let's triple the federal investment in R&D for energy, and they give the reasons why. So it's a very short thing. It's about 30 pages long. Easy to read. It's written to be easy to read. There's the URL, and I'd be happy to share that. And I would really recommend that you take a look at it just to kind of get a policy education. So let me start with the problems and the drivers. And the first one, actually the first two, are here. Here's a plot of the U.S. oil consumption and production since 1950. And you see back in the old days, we produced about as much as we used. This is sort of the time, 1950 going forward, when the interstate highway system was built and cars became an integral part of American society. Many of us moved to the suburbs. We built interstates that would take us there quickly. And now, in a sense, we're committed to that lifestyle because that's what the infrastructure is. So you need cars, especially in the U.S., much more than you did in 1950. And you can see the top curve. Well, let's take the bottom curve first. Production curve peaked in about 1970. This was famously predicted by M. King Hubbert. Everyone ridiculed his prediction in the 1950s. He used some very simple qualitative arguments to say that U.S. production would peak in the 1970s, and he was right. And people have taken him quite a bit more seriously since then. Turns out that doesn't make it any easier to predict when world oil production will peak. There's lots of arguments about that. But it's clear that it has to at some point, and this is what happened in the U.S. The curve is going down, and it's going to keep going down. There's no way to reverse that curve. So even though there are discoveries, and somewhere in here is the North Slope of Alaska, it's one of these little peaks. It does make a difference, but the general trend is down. The other curve is just the opposite. Consumption goes up, and you see some notable dips here, and in fact it's a little hard to see here, but because of the recession there actually is a dip here which might turn out to be as big as this one as we go forward. But generally the trend is up, that reason that trend is up is transportation. So 67% of all oil, whether it's domestic or imported, goes out the tailpipes of cars. That's what we use our oil for. And driving and freight on roads is now an integral part of the fabric of our society. It's not going to change. And that means that anything that threatens that ability for transportation has to be taken seriously. So you see the divergence of these curves. 2008, we imported 60% of oil. And so a great deal of that oil, about half of it, comes from the Middle East, parts of the world that are not necessarily very stable geopolitically, nor are they very friendly to the United States. So that might be something to worry about. And that leads to these concerns here. There's the problem that the supply might be interrupted for reasons like weather or some natural disaster or just a geopolitical decision. There's also the concern that it's unpredictable. And when things are unpredictable, it makes it hard to plan. So that means the government can't plan easily. Businesses can't plan easily. Prices go up and down. Supplies go up and down. And that makes everyone think in the short term. So you're not sure what's going to happen long term, so you better make your short-term plans. So that's a very negative trend. The other concern is the cost. So 60% of our oil, and you can see here's how many million barrels per day that is. You multiply that by the cost per barrel. It's about $350 billion a year that goes offshore. And that's money that is not stimulating our own economy, stimulating somebody else's economy and creating jobs somewhere else, but not at home. And we really need that economic activity here to recover from the Great Recession. So that's about $1 billion a day. So these are the two first concerns I wanted to mention. And here comes the third one. So it's greenhouse gases and climate change, and probably I don't have to spend much time on this. But here's a couple of 3 plots of data from IPCC, 2007, that's their last assessment. Here's the global average surface temperature, and you see it looks kind of flat here from 1850 to 1900. Then it certainly has a trend up. You can't deny that. Here's the global average sea level, an even more obvious trend up. Here's the northern hemisphere snow cover, not quite so dramatic, although this only goes up to early 2000s. It actually goes down a bit more dramatically after that. But the trends are clear, and this is not modeling of the future. So this is the past. These are measurements. That's what it did. So there is a trend for global warming. Most people agree that humans contribute to that by putting out greenhouse gases, in particular carbon dioxide. And these are the two biggest sources, coal-fired power plants, and they're roughly equal in magnitude, not quite, and the emissions from cars. And that accounts for about 2/3 of the carbon dioxide emissions. So if this continues, these trends continue, there's the threat of, the threat of climate change, which you can all imagine what that might entail, permanent changes in weather patterns, agricultural networks, coastal geography. That could be rather expensive if it's allowed to go unchecked. And in fact, the cost of preventing that by mitigating the carbon emissions is probably lower than the cost of adapting to it after it happens. So those are the drivers. And we've known since the 1970s, that was the decade of the first 2 oil shocks, that oil is a problem. And all of these problems are, in fact, serious. And not much has happened. So in the 30 or 40 years since, depending on where you count, since those oil shocks, we haven't made much progress. And there's a reason for that. The reason is on the yellow box there. Fossil is cheaper. Most people, institutions, households, countries make their decisions based on economics. And if you can get your energy cheaper from fossil, that's what you do. So that's has a good and a bad side, that message. It tells you, first of all, why we haven't done better, and it tells you what we have to do if we want to displace fossil with more sustainable energy sources. And there's some good news here, that's in this line, that most of the alternative energy sources are in their infancy. So they haven't been around very long. In fact, many of them were launched in a serious way just from the 1970s. So they're not very well developed, and they have a long way to go. So they can perform much better than they do now. They're way below their ultimate potential. That's different from the fossil industry, which has been around for 150 or more years, and some of it performs close to its theoretical limit. So a combined cycle natural gas electricity generation is 60% efficient at its best. That's close to the Carnot limit. By contrast, the best commercial solar cell you can buy is 20% efficient. And we know in the lab how to make solar cells 40% efficient, but they're just too expensive. So there's a lot of headroom, and that's basically a science problem. It's a materials problem, a chemistry problem, and a basic science issue. We don't understand the phenomena well enough to make the improvements, and that's where the opportunities lie. So here's the same message. Let me hurry through it. The bottom line, breakthroughs are needed to understand and control the materials in chemistry at molecular and nanoscales. So now, what is sustainability? As I was saying earlier, we love it. But what is it really? I'll give you 3 criteria and let you decide which you think is appropriate. Here's the first one. Lasts a long time. So oil in 1900, let's say, we weren't using very much oil. We didn't even know how much we had. It was cheap. And why worry about it? It seems to be the answer to the problem. You might think the same about coal in 2011. So, you know, there are hundreds of years of coal out there, especially in the US alone. So why worry about it? Well, we found out that oil, in fact, is limited. U.S. production peaked and world production will peak sometime. And we may be finding that for various reasons coal is not such a good source of energy as we might have thought. Here's the second criteria, does no harm. And I put two things under that, nuclear electricity because there's no CO2 production, that's great. And in fact, we understand how to make nuclear reactors. They've been around for a long time. So we could, if we wished, deploy, let's say they account for 20% of our electricity. Now we could deploy an equal amount of reactors and get it up to 40%. However, they do produce spent fuel, and we don't know what to do with that spent fuel. So this is one of the things, and of course since last March, people are much more worried about simply accidents with nuclear reactors. And there's kind of a, you have to weigh this. No CO2, that's good. Spent fuel, that's bad. Risk of accidents, where do you come out? The second thing I put was ethanol. I should have written corn ethanol. So you would have thought 5 years ago or maybe 7 years ago that there's not much, that it's nearly carbon neutral. And that seemed like a good idea at the time. In fact, it was written into laws in 2007, became official policy, legal policy of the United States, that a certain amount of corn ethanol would go into our transportation fuel supply. We now know that that's not such a good solution. So through life cycle analysis and more carefully looking at the situation, we realized that both the carbon footprint and the fossil fuel footprint of corn ethanol is not so different from gasoline. Remarkable statement, but that's true. We could have known it a long time before. We did know it if we just carefully looked at all the science, but that's the case. So there are other ethanols, cellulosic ethanol and other kinds of biofuel that might be better bets. Here's the third and most difficult criteria, leaves no change. So in this way of picture, all the outputs of the energy production and use chain are cycled back to become inputs somewhere else to leave no chemical change on the Earth. That's obviously, if you can satisfy that, you satisfy the other two, and that would, in a sense, be the most stringent definition of sustainability. I put two energy carriers there, electricity and hydrogen, because each of them has the opportunity, at least, to satisfy this leaves no change condition, at least in the operational sense. So you might ask yourself, now here's our sustainability profile, lasts a long time, does no harm, leaves no change. Is there anything that actually satisfies those conditions? And there is. It's something we all know. It's solar energy. So think about this cycle. A photon from the sun hits a semiconductor, excites an electron up to the conduction band. It goes through some wires. It does some work, and the work that electricity can do for us is remarkably versatile. It's remarkably diverse. And that when electricity does its work, it comes back, the spent electron, through these wires in the grid, replaces the hole that was created in the semiconductor, and the cycle is closed. So you don't see any chemical change left on the Earth. There is a change, however, and that change is there's one less photon in the sun. So the sun's been around for about 5 billion years. It'll be around for about another 5 billion years. So that's a long time, but it's not an infinite time. Even the sun is not sustainable in the most strictest sense. It's a long enough time that we might say we don't have to worry about it. Other things will happen first. But nevertheless, it's important to keep that in mind. So how's the profile? Lasts a long time, as long as the sun. That's pretty good. Does no harm. Yep, that's good. Leaves no change. It's a fully sustainable energy chain, at least in its operational form. Now, true, you do have to build the infrastructure. You have to build the solar cells. You have to build the grid and some other things. So that produces CO2 and uses energy, and you have to take that into account. But apart from that, it's fully sustainable. Nevertheless, we're not there yet. We're not doing it. Why not? Because we need some breakthroughs. We need lower cost, higher efficiency photovoltaics, so-called third generation materials and nanostructures, things that we're working on now but aren't there yet. And very importantly, you need electricity storage. If you're going to run, say, 50% of the electricity from the sun, you have to do something at night, and you have to do something on cloudy days. And we haven't really begun to think about the storage problem. So that's also a basic science question. So what about other potentially more sustainable energy technologies? Well, there's carbon sequestration. So here's the energy chain for that. You mine coal, looks like this in most cases. There are hundreds of years of coal. That's great, not quite as long as the sun, but a long time. You burn the stuff in power plants, what most of it goes for. Instead of emitting the carbon dioxide to the atmosphere, you capture it and stick it underground. And underground, it has to stay for thousands of years. And the reason for that is that the ultimate repository for carbon dioxide is the deep ocean. It can really handle a lot of carbon dioxide. We can put all the stuff that we're burning now down there. But it takes a while for that to happen. And the way carbon dioxide gets to the deep ocean is through the thermohaline current, so the conveyor belt. So the currents run along the surface of the ocean, pick up this carbon dioxide, dive down at various points up near North Atlantic, for example, and come back deep under in the deep ocean and circulate throughout all of the Pacific and the Atlantic and so on. That cycle takes about 400 to 1,000 years to complete. And if you're going to really store your carbon dioxide there, you have to wait several of those cycles, trap it for several of those cycles, to make sure that it doesn't come out and affect the environment. So that's a long time. That's a real issue. Also, we don't really know what will happen to the carbon dioxide that goes underground. So we used to think, well, we'll put the carbon dioxide in the atmosphere. There's plenty of room in the atmosphere, no harm at all. It'll be fine. And we realize now that indeed there are unintended consequences, global warming, but it's kind of the same attitude. Let's put it underground. What could possibly go wrong? Well, we don't know. So there are about 12 or 15 different rock environments underground that this carbon dioxide is going to interact with and react with chemically. It's going to be at high temperature. It's going to be at high pressure, supercritical. And those reactions will be different from what they are on the surface of the Earth. You have to worry about where it's going to go. The rock underground is porous. That's why there's room for the carbon dioxide. But that also means that the carbon dioxide can migrate. And you need to know that over this period of 1,000 years that it doesn't migrate somewhere where you didn't expect and pop up again in a leak where you didn't expect. So there's some basic issues that need to be resolved. How's the profile? Lasts a long time, hundreds of years, not as long as the sun. Does no harm? Well, no CO2 emissions, that's good. On the other hand, you're putting carbon dioxide underground and you don't know what that will do. So that's maybe a mixed bag. And leaves no change. No, that's not the case. You're taking coal out of the ground and putting CO2 back in, so it doesn't satisfy that criteria. Here's what you need, most of the things that I've already mentioned. What's the chemical reactivity with the rocks in extreme environments, high temperature and pressure? You want to follow the migration through porous rocks, and you have to do that remotely from the surface somehow. You need geologic monitoring and predictive modeling for what will happen, and you have to worry about leakage routes to the atmosphere. So think of it this way. If you have a leak rate of 1%, then in a century, all the CO2 that you put underground in the first year has leaked out. And a century is just a blink of an eye in global warming timescales. What else could you do? Well, here's nuclear electricity. Uranium is mined pretty much like coal, looks like this. You put the uranium in a reactor, no CO2, that's terrific, but you do have spent fuel. What do you do with it? The preferred solution worldwide is to put it underground. We were going to do that in the United States in Yucca Mountain until the Obama administration came along and said, no, we'll take another route. We don't know what that route is yet, but I think there are some studies going on that are just about due now to report out. This is a cartoon of the Yucca Mountain site. It's very simple. There was a tunnel in the mountain. The tunnel was about 300 meters beneath the surface to keep it out of weather. It was about 300 meters above the aquifer to keep any leakage out of the water supply. And this spent fuel was contained in cylinders, concrete, steel, various things, and put there. And one of the biggest issues, as we realized with Fukushima, is that it's hot. So because the stuff is decaying, it takes hundreds of years, basically, for the temperature inside this cavity to reach its maximum and then to go down. And you have to worry about that heat. So the design engineers have figured that out. And they have this proposal that has so far been turned down because nobody wants it in their backyard. So what is now you have to store it there for quite a long time. We said thousands of years for CO2. The radioactivity in the spent fuel can be tens of thousands of years. That's a pretty long time when you realize that civilization itself is only 10,000 years old. So how would you possibly ensure that it will be safe? And that's really a wonderful question. The profile lasts a long time, well, hundreds of years, not as long as the sun. Does no harm. It's a little bit like CO2, so there's no CO2 emissions. That's great. But you do have spent fuel, so what do you do with that? And certainly does leave change. You're taking uranium out of the ground and putting putting spent fuel back in. Here are some of the things we need to do. So all the reactors we have now are 1960s vintage. That's when they were designed, and we don't have really anything newer. Technology is a lot better. So we can now operate at, say, 50% efficiency instead of 30%, as we did in the 60s, by raising the temperature. To raise the temperature, you have to raise the neutron flux. That's how you get the temperature up. So you have to find materials that can withstand the higher temperatures, the higher neutron flux, and actually the high corrosivity. So even water at those temperatures is quite corrosive. And so we can do that. We can make those materials now, and we can make reactors much safer, passively safe, as they say. But that remains to be done. So those are the challenges. And there's geologic monitoring and modeling, much like the carbon dioxide that would be underground. Well, what else can you do? You don't have to use conventional oil at all for car. You could use biofuels. So here's switchgrass. That's how much it grows in 1 year, which is a lot. You would then try to convert the cellulose that's in the leaves and the stalks into ethanol. That's tough. You would do it like this. This is actually a corn ethanol plant, but wouldn't look much different. And we don't know how to do that. That's a tough problem, to break down cellulose and lignin and the other components of plant cells. And it's expensive. So there's plenty of research going on now, bioenergy research centers that are funded to do that and have been for maybe 3 or 4 years. So that we may get the breakthroughs that we need. You would then burn the stuff in your engines, and the CO2 would come out of the tailpipe, go into the atmosphere, but be recycled back each year into the next crop of biofuels. So that's kind of this line. There's also another opportunity. You could make solar fuels without biology. So you could artificially mimic what biology does with chemicals that you find in the laboratory. And this is an old subject, a couple of decades old, if not more, called artificial photosynthesis. And remarkable progress is being made, and it's actually a fascinating subject. Not yet ready, I think, for anywhere near ready for commercialization. That uses the photons from the energy in the photons from the sun to create electronic excitations and do chemistry. There's another way to use the sun's energy, so thermal conversion. You can concentrate the rays of the sun and create temperatures of, let's say, 1600 degrees C in a furnace. And at that temperature, it turns out a lot of the reactions that either split water or reduce carbon dioxide to carbon monoxide and hydrogen, usually, go a lot faster, and they go in the right direction, and you can just use that thermal energy. So it's not at all biological. It's just ordinary, let's say, physical chemistry. There's a third opportunity, and that's the oil sands that we now get from Alberta in Canada and shale, so heavy oil. And you can, or you could even use coal. You could make coal to liquid, as they do in South Africa. There's an issue with that. It's full of carbon, these oil sands and shale. And there's something like 50% more carbon dioxide emissions from this stuff to produce a gallon of gasoline as there is from conventional oil. So you're getting a lot more CO2 that you have to do something with. And there's a lot more toxic things and things that you really don't want, pollutants I've put here, that you have to deal with. So what's the profile? Well, for cellulosic biofuel or solar chemical fuel, it's pretty good. I'm probably minimizing some water issues there, but in principle, you could solve them. For oil sands and shale, the outlook is different, lasts a long time. Well, there might be as much unconventional oil as there is conventional oil. So you might get a factor of 2 in the total supply. So that helps, but still finite. Does no harm? Nope. You get lots of carbon dioxide emissions and certainly cannot satisfy, leaves no change. So here's some of the breakthroughs I've already mentioned. Cellulosic breakdown to sugar and fuel. And the chemistry of carbon dioxide to fuel, that's even tougher. Problem that probably can be solved, but it's a difficult chemical problem. What else can you do? Well, you don't have to run your car on any kind of liquid fuel. You could run it on electricity. And there are 2 ways to do that, as shown here. But first, let's just take a look at the motor. Picture of the Tesla Motors motor. It's not very big, pretty small. And look how simple it is. It's a housing, a stationary housing with a coil on it and a spindle on the inside which rotates. Nothing else moves. Compare that to a gasoline engine where you have to have a valve which opens to let some fuel in. The valve closes, the piston is moving up and down at just the right moment. You need a spark which explodes the fuel, pushes the piston down. You open another valve, spent fuel goes out. Spent fuel is toxic, so you can't let it go into the atmosphere. It has to go over a catalytic converter. But we know how to do that pretty well. And in the last 100 years, we've really perfected is the wrong word, but dramatically improved gasoline engines. And they now actually run remarkably well and much better than they did 20 years ago. But if you were going to start now and say, I want to make a personal transportation device, should I go with gasoline or electricity? You might decide to do it this way. There's one other big advantage to electricity, and that is motors are typically 90% efficient or more. Gasoline engines are typically 25% efficient. So there's a huge, just how much fuel are you using at the point of use to produce the transportation. So if you're going to use electricity, there are 2 ways to get it. One is put a battery on the car, and the battery drives the motor. The problem with that, or the challenge with that, is the battery itself. They're not very energy dense, so we need to make much more energy dense batteries, maybe a factor of 2 or a factor of 5 to increase the driving range. You have to charge the battery from someplace, so the idea now is to charge it from the grid. And if you wanted to charge it at night only, actually wouldn't be a dramatic burden on the grid because the grid produces during the variation in in our generation is about a factor of 2 between late afternoon and overnight. So there is capacity to do that charging. If you want to charge during the day, it might be a different story. And you have to produce that electricity somehow. So if you produce it by burning coal, you haven't done much for the carbon dioxide emission, it turns out, if you look at the whole chain. But there are lots of other ways to produce electricity. The other way is to use a fuel cell. It's still an electric car. You produce the electricity on the car through a fuel cell with hydrogen and oxygen. Producing water is the output, and you produce the electrons through this pathway which go through the motor and turn the car. If you're going to do that, you need a way to store hydrogen on the car. That's a tough problem. You want actually hydrogen stored at densities greater than liquid hydrogen. That sounds like a tough issue, but actually it's pretty simple. Turns out liquid hydrogen isn't very dense, and there are lots of materials that are able to do that. The problem is that if you store at a high density, usually the hydrogen is very well bonded, strongly bonded, and it's hard to get it off. So you need a high temperature or some other trick to release it for use in the fuel cell. And just as with electricity, you have to get the hydrogen from somewhere. So right now in this country, 90% of the hydrogen is produced by reforming methane, CH4, and that does, it turns out, nothing, or almost nothing, for the carbon dioxide production. This chain would produce about as much carbon dioxide as gasoline. So what's the profile? Well, lasts a long time, does no harm, leaves no change. In principle, and I've glossed over a few things here, but in principle, you could solve all these problems and make it come close to satisfying all of those conditions. The challenges and the breakthroughs that we need: 2 to 5 times higher energy density in batteries. And we need, for the fuel cell route, catalysts, membranes, and electrodes in in fuel cells. So that's it for the energy technologies. Now let's look at some technologies that we'll need in order to access some of these more sustainable ways of supplying energy. Here's the grid taken from space. You can see that where all the power is being used by the white lights on it. And if you ask the following question, we have a lot of renewable energy in this country, a lot of wind and solar. Where is it? So the wind is typically in a band that goes even a little bit farther south than this at mid-continent. It has to do with partly the topography of the continent. The sun is in the southwest, and the people are pretty much east of the Mississippi, and some, not to insult Santa Barbara, some along the west coast. But those where the people live is far from where the renewable resources are concentrated. So that means you need a way to get the electricity that would be produced locally here from the source to the market or to the market over here. And we're not set up to do that. So our transmission system in this country was built on the assumption of local use. So you wanted to produce by fossil electricity maybe 10 or 100 miles outside of a city and ship it into the city and you're done. We can now, because every population has grown, cities have grown, and the grid has grown, you can now connect those local grids. They are connected. And in fact, you can ship electricity across the country, but it's a little bit like driving across the country before the interstates. So you could go from New York to Los Angeles. It's tough, it's slow, it's inconvenient, it just doesn't work very well. We need an interstate highway system for electricity. That's what we need in order to realize this dream. So that's the bottom line here. This is what we need. Long-distance, reliable, efficient delivery of electricity. And what about this? This is an interesting plot. It's the energy storage density, either plotted as a function of energy per unit volume or energy per unit mass along this axis. And you see the two champions here, and in fact the one champion is gasoline. It's really great at storing energy in chemical bonds. And that is the reason that we drive around in our cars with gasoline in the tank, because there's a lot of energy there. Here's ethanol. It's not quite as good, but we mix ethanol with gasoline. We get the energy out of that by combustion. On the same scale, here are batteries. They're almost at the origin. So they just can't hold a candle to the energy storage density of chemical fuels. Nevertheless, they're more efficient, so this looks worse than it is. This is 90% efficient. That's 25% efficient. That cuts the gap here between the two. But it's still a rather large gap. And we would rather use the energy in batteries as electricity rather than as heat. And basically, a gasoline engine is a heat engine converting heat to motion. We'd rather convert electricity to motion. So a lot of people say, well, you can do better with batteries. The visionary people say you might do a factor of 10 better with a lithium-air battery. So if you put a factor of 10 around this point, you get that. And you see it is better, but still nowhere near as good as chemical fuels. So but there is a way to solve this problem. So imagine that you'd like to store the energy in chemical bonds, and you'd like to use it as electricity. But that's exactly what fuel cells do. So I've plotted here the storage density of methanol. Here's the target for hydrogen for fuel cells. Here's where we are right now with compressed gas. You see, still better than batteries. So you would store the energy chemically, and you would convert it to electricity, let's say, in a fuel cell. There's a tremendous opportunity for electrochemical energy storage and electrochemistry to fill this gap. So what do you need? You need 2 to 5 times increase in battery energy density, and if you do it with fuel cells and electrochemistry, you might get maybe 10 to 20 times increase. So let me make a couple of comments now about the differences between traditional fossil energy and sustainable energy. And in fact, materials are treated very differently by these two conversion routes. So first, let's talk about traditional energy. So the fuel is an input, usually one of these. So gas, oil, or coal. First thing you do is burn it. You want to convert its chemical energy to heat. And it's usually not the heat you want. Sometimes you do want heat, but more often you don't. So you then convert that heat through a heat engine into mechanical motion. That's what your car does. Or you convert that heat in a turbine to rotary motion and stick an electricity generator on the end of that shaft, and you get out electricity. So you actually, in most cases, don't want the heat at all. And the heat, of course, is the least efficient step in that conversion chain and the one that produces the most harmful environmental effects. But if you look at where the important materials are, they're the fuels. And you like these fuels because they're cheap and they have high energy content. That's what you like about them. They're not permanent. They are burned. They're disposed of in the first step of the energy conversion chain, so they're gone. You don't keep them around. And that's kind of the sense of the fossil energy chain. How about the sustainable energy chain? Well, it's very different. So first of all, the input very often is not a material at all. It's an unused energy flow, like sunlight or wind or something else here, or biomass, which actually is a material, but gets renewed every year. You don't burn these things. At somewhere around room temperature, you do a direct conversion. For example, if photovoltaic takes sunlight to electricity at approximately room temperature, you may have chemistry that produces biofuels and other kinds of fuels here, and you get your useful work out on the other side. So what are the important materials here? It's really this step that's important. So there are very high-tech materials in chemistry, a photocell, for example, or an electrode in a battery or a fuel cell, or a superconductor for carrying current, or a catalyst that's used for chemical conversion. And these things are complicated to understand. It's not like combustion where you simply explode something or ignite it. And it's there that the opportunity lies. So with sustainable energy technologies, if we can improve these conversion materials, we'd like them to last 30 years, photovoltaic, for example. And if we can improve their conversion performance, their efficiency, we have a chance to get the cost down. So here's the take-home message. Sustainable energy requires controlling complex functional high-tech materials in chemistry, and that's the challenge for the research community. So can we do that? Well, let me spend this view graph talking about that. Here's what we want to do in yellow, and here are 3 blue bubbles that indicate that maybe the time is right to do that. And let's start with nanoscience. We've had about 10 years of nanoscience, or at least the word nanoscience, and it's been remarkably successful. It's actually produced a lot of wonderful new knowledge and new science and new materials about how things work. And it's still in favor. If you go to Congress and say, by the way, this involves nanoscience, they'll say, oh, tell me more about it. It's remarkable that after 10 years it still had that patina to it. But it's actually taught us a lot. So we know how to make materials at the nanoscale, either by lithography or by self-assembly. We've developed tools like scanning probes to look at what happens on those tiny length scales and understand, at the atomic and slightly larger level, the conversions that take place. So in a way, this is 10 years, a decade of preparation for making the kinds of materials that we need. Let's talk about this one, it's computer modeling. So about 10 years ago, we passed the teraflop frontier. That is, we got machines that could operate at the teraflop level. Now we're passing the petaflop, and 10 years from now we'll pass, everyone says, the exaflop frontier. So in 20 years, that will be a factor of 1 million in computer hardware. That means you can model things that haven't been made yet. Millions of atoms, that's enough atoms to have some functionality. So you could simulate the functionality that you expect from a material that you haven't made. So right now you can maybe survey 1,000 different materials, eliminate 990 of them as not very suitable. 10 maybe look promising. You'll make 5 of those in the lab, and 2 of them will turn out to be useful. That saves an enormous amount of time over synthesizing all 1,000. So this is a tremendous opportunity to shorten the lifetime and be much more effective. complex materials, so there's a aphorism, complexity equals functionality, and the proof of that is biology. So the cell of biology has a tremendous amount of complexity to it. It has enzymes, it contains all kinds of materials. I mean, DNA is in there to tell it how to reproduce and make the next protein. And it turns things on and off in order to accomplish its functionality. So that's, in a sense, the paragon of complexity equals functionality. What we need to do is do the same, shoot for the same kind of complexity and functionality in inorganic materials. So we don't have to be quite as elaborate as biology is, but we can be much more elaborate than we typically are now, both in terms of composition and in terms of functionality. So it's a good time. We might actually, as we could not have done in the 1970s, solve some of these materials problems that are the bottleneck for sustainable energy. I think I'll skip this slide and tell you about these, you probably already know about them, these dozen or so reports that the Office of Basic Energy Sciences has put out since 2002. That was the one that I first got involved in. And they've taken every area of sustainable energy, science, and technology and status report. So where are we now? What are the problems we have to solve? And I think these reports have been essential to making the case that we need to do more R&D to enable sustainable energy. And they paid off in budgets. So for about 6 years, nothing happened. And it would have been easy to get discouraged, but BES did not get discouraged. They kept going. And around 2008 or so, suddenly the Energy Frontier Research Centers were funded, 46 of them. I'm sure, in my mind, others may disagree, but I think generally there's agreement that it was this groundwork, a decade, or at that time 6 or 7 years, of putting together the case that made everyone into believers. So there's that, and I mentioned at the beginning that there is, it's not just technology. There's a lot of richness to this area. So we've been talking about energy sustainability, and of course that's very important. Environmental sustainability, often these two are at odds. So the easiest way to produce energy may not be so good for the environment. And economic sustainability, which is on everyone's mind right now. Why don't we recover from the recession? And an even more important question, over the next 40 years, what will be the foundation of our economic growth, like cars were in the mid-20th century? What's going to take the place of those? And of course, very often, you want cheap energy to run the economy. That's not good for the environment. So you've got things pulling you in lots of directions. And you have to make a decision about this. So the way we do it in the United States is to elect representatives to the government, Congress, the president, and tell them what we think and hope that they'll make the right decisions. Sometimes it seems dysfunctional, not even working at all. Sometimes it does actually work. But that's how we do it. So I want to, I have 2 more slides. I want to, and I see this one this is fine. There'll be a couple of other things showing up here. What do we need to do? I think we need to do several things. So one is to educate the next generation for energy literacy. So professionals like us and engineers, scientists and engineers, they understand energy pretty well. Not a problem. We could be a little bit more interdisciplinary. So if you know only solar, you should also know something about nuclear, because it's one big picture. So we need to do that. But even more important, I think, for finding the right path is to educate people who are not experts. So regulators, government officials at all levels, city, state, federal, business people, so that they'll understand the technologies, the energy technologies that they're wanting to bring out, and urban planners, so that we can implement these technologies in a real way. And we need to educate private citizens, because that's us as citizens. We're the ultimate decision makers, and I've noticed this to be true the last 2 or 3 years. If you want to get Congress to do something, of course you should go tell them, but you ought to convince the public first and let the public tell them. And it's very important, I think, as private citizens that we guide our Congress people and our government officials in the directions that we think we should go. We also need to research and develop more sustainable technologies. That has been the bulk of what I was telling you. materials and chemistry of greater flexibility and functionality. And we have to consider policy. So if you have 10 new energy technologies, which is the one that you want to implement? That's a hard question to answer. And if you could answer it, you'd design some incentives to make it happen. But as Steve Koonin said once famously, the problem is not having new energy technologies, it's having a policy to understand how to coordinate those technologies. So we have to look seriously at policy. And finally, entrepreneurship. It's not going to be the big companies that take the risk to bring these new energy technologies out. It's going to be small companies, and we need to have culture, as we do have, but we need to sustain it and maybe promote it a little bit more than we are now to discover these new technologies and deploy them through small companies. So I have actually 2 more slides. One is this one. Is something that we launched last summer in Chicago. It was held in August for the first time, the UIC Summer Institute on Sustainability and Energy. And the idea was to do what I had on the previous slide, take 40 graduate students, we'd like to get that number up to 80 in the coming summer, give them an intense, in our case, 8-day, we may make it a 10-day immersion in energy and sustainability, lectures from people from the Chicago area and also around the country about climate, about energy technologies. And we take tours of energy and sustainability sites in Chicago and give each team of about 7, so we had 40, we had 7 teams of 7, or 7 teams of 6, I guess. We gave them challenge projects, solve a real world problem, and in your solution include technology, policy, entrepreneurship as the 3 elements of any solution. Don't tell us just admiring the problem. It's a tough one. We don't want information about the problem. We want a solution. And we want you to make an innovation in one of those 3 areas and use the other 2 to support your innovation. So it turned out remarkably well. I was impressed with how the students did. I didn't think they would do so well. They had a week to do this, and indeed, they did a great job. So here's my perspective in my last slide. Energy is making a historic transition from fossil to alternative to clean and sustainable. It's going to take decades, so this is a long-lasting activity. The bottleneck for most of these new energy technologies is the basic science understanding of the phenomena. It's not necessarily engineering. Of course, there's plenty of challenges there too. And here are the things that we have to do, as I was saying on the last couple of slides, to successfully come through this transition. So with that, I think I'll end. Thanks.
Somehow change the voters, because I know a lot of people in this community who I talk to, who are not in favor of a certain set of things that I think we need to get there. How do you think this is going to happen, and how long do you think it's going to be?
So I think So I think one of the secret weapons is the next generation. So I've noticed students really like this, and in fact many of them would rather do this than what, and I mean PhD students, rather than do this than what they were set out to do. And if you look out at the general population, I taught a course last spring at UIC on, it's called Energy for Future Decision Makers, not at all technical. You had to know arithmetic and that's all. And the students were really supportive of it. So it may be like the environment. It kind of took, from the 70s on, it took the next generation to believe it and to make it happen, and 20 years later, indeed, it did happen. So I think that's a good secret weapon. But I think you're right. It has to get really bad before people will take it seriously. This administration is taking it seriously. Obama says all the right words, and he basically says what I said. I'm sure he didn't get it from me, but I fully support that. I think he's got on the right track. He's running into some issues, and I know there are people in the community who don't agree with some of these things. In fact, maybe global warming is the most difficult one to sell now, just because of the way things are in the last few years. But there are other drivers, like the economy, that everybody wants to have come back. And if you believe that developing alternative energy technologies will make that happen, you've got a believer class there. So that's my answer. There's a question back there.
So, as strange as it may seem for us coming from a technical background, there's resistance to these kinds of
Right.
changes from special interest groups, big oil companies, coal companies, the kingdoms in the Middle East that want our $350 billion a year.
Right.
How does that play into the roadmap towards a sustainable energy future?
Well, these things are, and I mean, that's the way we make decisions in this country. So we have a government that is capable of tilting one way or another. Historically, it's mostly tilted toward fossil fuels. That's been the history. It looked last year, I guess it was, or was it 2 years ago, like Waxman-Markey might even pass Congress. It passed the House, that there would be a cap on CO2, or at least some control of it. Fell apart. I think it would be too pessimistic to say the special interests will always win. So there are some common goods. Usually special interests don't care about the common good. They care about their own good. We did it with air quality. And somehow there was no special interest that was really in favor of that. And yet, over a 20-year period, the air is remarkably better than it was, and I think everybody's happy. The world didn't end. You hear about the cost of this, the cost of CO2 caps. It's going to make everything more expensive. The economy's going to tank. We'll lose jobs and so on. Those arguments you hear all the time. And I would say that one has to look at them rather carefully. Because the good, the ultimate cost of CO2 emissions is being paid by somebody. It's not being paid by the special interest, but it's being paid somewhere. And it's in the end, it's the total cost that you want to minimize. So I don't know. I would be optimistic. I think it's mostly a matter of attitude. So it's hard to make the argument that this will happen in a certain time or it won't. But I would be optimistic. It's like, cigarettes cause cancer. Well, yeah, they do. It took a while to convince everybody, but they do.
It seems like, given the economic situation you described, that the way that we're going to make this transition is either to make fossil fuels more expensive or to bring down the cost of renewables now, or sustainable, if you should say. So, I mean, that either is by scientific progress with funding research and development, or it's on the side of taxes and whatnot. And if those two things are never equilibrated, then there will be no transition. So I guess I'm wondering if you can sort of comment on the tension between trying to pick technologies that look promising versus pricing the things that you really care about, for example, greenhouse gases or dependence on stable energy sources.
So take a look at this report, which I had on the second view graph. It was the one on the right. You'll find there a 30-page summary of why it's important to do those things. So you've cast, and most people cast, the question in terms of economics. If it's not cheaper, it's not going to happen. To a certain extent, that's right. But I think there are other drivers too, and such as economic competitiveness. So I said the economy is a big driver now. So is economic competitiveness. Look at China. You can name other countries too. They're spending more than we are. They're actually moving faster than we are in terms of developing the alternative energy technologies. And that's something we need to worry about. So this report that I referred to, in fact, makes the case on that basis. And it says that we just need better educated, smarter, more innovative people. And if you think that the world is eventually going to be flat in terms of who can do what, everybody that has the manpower can do it. Well, China will win. There's no doubt about that. But if you think that innovation is important, then you could have those innovations coming from the United States and slowly migrating off to other places, but you'll have 5 years or some time period to develop them and keep the edge. So it's a very selfish point of view, and there are many sustainable philosophers who would say that'll never work because ultimately the world is one, it's one unit. But for the foreseeable future, that's a way to stay ahead.
Is there any research or weight in reducing the consumption that we're going to require, or do you
Oh.
just accept that that's the way that we can?
So that's a great question. And indeed, there's plenty of evidence that we can get along on less. So US uses twice the energy per capita of Europe or Japan. And right away that tells you why. You'll find a lot of defenders, oh, the country's colder, it's bigger, we need to need more transportation and so on. I don't think anyone's ever done a careful analysis of why that is. But there seems to be a proof of principle that indeed we can live on less. And it's certainly true that if you ask right now, what's the biggest source of energy? It would be energy efficiency and conservation. We could just use less and we would get that as free energy. So that probably has to change. That's a lifestyle question. It's pretty hard to legislate that. People have to volunteer that that's what they want to do, or the price has to be so high that that's what they're forced to do. But there's certainly a lot of headroom there. And that's, in the short term, more important than the R&D we could do. In the long term, they might not be so different in their impact.
I had a question about your diagram
Yeah.
where the fossil fuels, chemical fuels look so good, batteries look bad. Fuel cells look good. Hydrogen storage is an issue. Methanol-powered fuel cells are available. Why are we not using them?
They are being used in some, not for cars, but they are being used for some other niche applications, like forklift trucks and things that don't have to go very far, and you can come in for service whenever you want. But there's plenty of room there for more, and I agree. I mean, to me, that's a wonderful opportunity that's waiting to be exploited.
Is there a specific bottleneck technically to have them more widespread?
I mean, fuel cells have a few issues. They're pretty expensive compared to a gasoline engine. I mean, a lot more expensive. They're not as durable, so it's nice to use them indoors rather than outdoors in a cold climate. You guys don't have to worry about that, but we do. And they don't last a long time. So those are some issues that are around. And I think back in 2003, George W. Bush said, the babies being born today will drive hydrogen cars in 20 years for their first car. Well, that was too optimistic, and we all agree that that was too optimistic. But that could be out there as a longer-term solution. I think what happened is people realized the infrastructure challenges of hydrogen or methanol for fuel cells in cars are completely irrelevant if you use electricity from the grid, and we already have that infrastructure. So it's much easier to have electric cars that you charge from the grid, and things can evolve from that.
Yes, but then you're stuck with the batteries, which are
Yes,
important.
absolutely, that's right.
Have you seen any work or studies related to ammonia as a
Yeah,
energy storage medium? Is that any less or more promising than methanol, for example?
so people in Europe are actually developing that. I don't think it's not such a big deal here. We don't talk about it so much. But you can use ammonia directly in fuel cells, for example, in solid oxide fuel cells as a fuel. And we understand ammonia. There is an infrastructure and a technology base for it. So it does have potential. It has some issues. I mean, ammonia is not something you want to come in contact with, but it's probably worse than gasoline. But it does have issues. It does have potential.
As somebody that's been a little bit opposed to the alternative fuel, which I appreciate the opportunity to hear everything you said today in such a straightforward manner. Part of the problem, I think, is that some of this information is not really known to the general public, and a lot of misconceptions with popular media, et cetera. My question to you is this. I know from your background, you worked with Argonne National Lab. Why doesn't the federal government promote a policy that utilizes the infrastructure already at existing companies that, with their R&D departments, to incentivize them to develop some of these breakthroughs in the basic areas you're talking about, so that they could be more readily achieved in addition to the
That's a really good question. And in fact, I didn't emphasize it, but it was implicit in what I said, that a lot of these technologies, they face plenty of engineering challenges, and there are a few gaps, few bottlenecks that are really basic science. The companies that you referred to just don't do basic science anymore. So Bell Labs closed down, IBM has changed dramatically, Ford has changed dramatically. They take a much shorter term view. They don't want to invest in something that they're not sure is going to pay off. So there needs to be another place for that stuff to come from, that kind of research. And I think DOE recognized this. One of the reports that was up on that list of 12 was a thing called Science for Energy Technology, which is now a year and a half old. And the idea of that report is that there are basic science gaps in the technology development chain that require basic scientists to solve, and that companies ought to engage with basic scientists to identify those gaps and solve them. You don't want the basic scientists doing technology. They're no good at that, but they can solve these, fill these gaps that are missing, and that should be a way of the future in order to achieve some of the things that you're talking about. They do, on a different scale, there are incentives for the companies that you mentioned for alternative energies, and the government is looking at those things. So, and for example, for wind. So wind wouldn't be where it is. It's growing at 40% a year, but it wouldn't be where it is if it wasn't for the production tax credit, which just barely makes it profitable. And when that in fact, that production tax credit has gone off 3 times during the last 20 years, and each time it's gone off, the growth has leveled in the wind industry. Then it would get reinstated, and suddenly it would go back up. So it's quite clear that that's very important, and they need to do that. It's a longer discussion, but I'm not sure it's a good idea to do that forever. You have to eventually get these technologies able to compete on their own without an incentive, or you haven't really gone anywhere. Well, there's some universities that really excel at that. So I actually learned today that UCSB is doing pretty well, and that it intentionally and strategically goes out and does that. I think that's wonderful. MIT does that really well. Stanford does that really well, and you could name a few others. The Research Triangle is doing that pretty well. Probably need more of that, but it's not for everybody. I mean, not everybody can do it. There's not the critical mass there. There's not the, the connections available for it to happen. And I think it's a mistake for every city that wants to have a economic development zone to say, well, we'll put an incubator around the university and that'll do it. It doesn't happen that way. You need a critical man. You need some people with the experience. So we probably need more than we have now, but maybe we need a factor of 2 more or something like that, but we don't need everybody to do it.
Okay, well, we should probably close now. Thanks again for a really wonderful talk and
Thank you.
answering all the questions. That was great.
Thank you.
Pleasure to.
Hi.
Hi, Michael Ditmore. Are you at Champaign? Are you
Hi.
at UIC?
UIC in Chicago.
In Chicago.
Yes, so it's University of Illinois Chicago. The one in Champaign is called UIC.